And you come in basically, and then you can see the full experiment. So it's kind of the size of a building, but still you can see kind of with one view you can see it. So it feels like it's a really, really large tabletop experiment. And that's, I think, the feeling you get out of g-2. And that's also one of the beautiful things about g-2. It's still simple enough so that you can have the feeling that you understand most of the parts.
Muon g-2 is studying a property of the muons. What are muons? They are subatomic particles that are in some senses similar to the electrons. They are present in our lives because they rain from the sky continuously because of cosmic rays. We are now still studying them because they have still surprises in their behavior.
So the standard model of particle physics is essentially the collection of all the knowledge we have today about particles. It's kind of a mathematical framework, but you can just think of just all the particles we know and the interactions are described in this theory. We test the standard model through this experiment by using the standard model to predict this quantity, the g-factor of the muon, which basically describes how the muon, this particle, the spin of the particle, interacts with the magnetic field that's present.
Everyone gives this example like spinning top, which does this spinning around it and also wobbling caused by the magnetic field in the environment. In the experiments that were conducted over the years, we found out that it is slightly different than 2. That's why it is called g-2.
So muon magnetic anomaly was actually a number that theorists were waiting for a long time. I mean, the last measurement was done by Brookhaven at the beginning of the 2000s. So theorists were waiting for an improved version of the experiment.
So in 2013, I was doing my PhD studies. One afternoon, I heard that there was a big magnet coming in at the lab. There was a lot of people at the lab when the ring arrived, and I was so fascinating because they were expecting to measure a quantity so precisely. So in 2021, the Myon g-2 experiment published their first result, and was our first milestone.
Then in 2023, that's our second publication, where it's run 2-3. We measured twice as precise as we did before.
This final result will include all our data from run 1 to run 6. So we are including run 4, 5, and 6 that we take in the past few years. And the final publication will be the most precise measurement of the anomalous magnetic moment of the muon.
We would like to reach to 140 part per billion sensitivity.
I think that still, for me, it's a little hard to understand what that really means. Another way to think about it is kind of in time. So I'm 36 years old, and kind of for my life, it would basically be measuring the whole life I have lived so far to a precision of 2 minutes, which kind of feels quite impressive to me.
In physics, every time we measure something, we also estimate the uncertainty of the measure that we perform.
We have two kind of uncertainties in Myon g-2 experiment and in all of the experiments, basically. One of them is the statistical uncertainty.
In the case of g-2, how many muons we are able to track and collect in our detectors.
The final publication of Myon g-2 with the run 4 and 5, 6 contains 75% of the total statistics of the experiment.
So each time Fermilab accelerators send us muons, we can store about 5,000 muons in our storage ring. And when we check the numbers for run 4, 5, 6, that comes to above 1 trillion muons that we stored.
The second type of uncertainty, we call them systematic, and are relating to the way that we gather the data.
Precision is a critical component of the experiment, because when you compare numbers in particle physics, you don't have just a number, but you have a number plus its error bars. So for example, if you use a measurement tape to measure the length of a table, you can go as precise as your ruler have markings. So this is why you need an uncertainty associated to the value you want to measure. It tells you how precise your instrumentation is.
In the second half of the experiment, we implemented a few new subsystems, which eventually helped us reduce our systematic uncertainties. Eventually, g-2 is trying to measure this quantity as precise as possible. So as you collect more data and give more results, we combine all those results from run 1, run 2, 3, and then run 4, 5, 6. We combine it even with the previous experiments which were done at BNL. So that gives us the world average number for anomalous magnetic moment of muon, which eventually will be compared to the theory prediction.
We just had an incredibly intense and exciting meeting of the whole g-2 collaboration because we just unblinded for the first time our final result to see where it landed. The 456 result really rests on the shoulders of the previous two publications that we've had. It's our largest data set, it's our best data set, and that's reflected in the fact that we've managed to keep our systematics under control. The muon g-2 experiment has just measured a mu for the muon to be 0.001-165-920705. And we've done that to a precision of about 127 parts per billion. At the top of the plot, you can see the result from Brookhaven from 2006. That was the result that was in tension with the standard model prediction that launched our whole enterprise at Fermilab. Following that was the result from our first year of running at Fermilab. Next, you can see that we've shrunk our error bars considerably when we looked at runs 2 plus 3 results, and now even smaller error bars with our final result from runs 4 through 6. Below that result is the combined average for all 6 years of our running, and at the very bottom, the new experimental world average. And it was really exciting and thrilling to see it land right in agreement with our previous results. When we look at the standard model, our description of particles at their most basic level, there's still some really basic fundamental questions that we just don't understand the answer to. Now, our theory colleagues try and address some of these questions by introducing new symmetries into nature. Along with new symmetries come new forces and new particles. And we've made such a stringent measurement that their new theories have to agree with our result. They can't perturb the strength of this magnetic field too much from what we know from the standard model particles. We're really excited to have our paper submitted, and we're really looking forward to letting the world know what we've done.